taking a look at problem 4, we're given this table and they tell us that the height of tree at time t is given by a twice differentiable function h, where h of t is measured in meters and t is measured in years. Selected values of h of t are given in the table above. And it says use the data in the table to estimate h prime of 6 using correct units, interpret the meaning of h prime of 6 in the context of the problem. So h prime of 6, that is my instantaneous rate of change, but I know that I can approximate that by looking at the average rate of change, which would be the behavior on either side of 6. In other words, taking a look at what's happening at t equals 7 and what happens at t equals 5. So I can say that it's approximately equal to h of 7 minus h of 5 over 7 minus 5. So I can say that that's 11 minus 6 over 7 minus 5. And using correct units, keep in mind that we're talking about a change in meters over time. So this is meters per year. So in other words, I could say the tree is growing at approximately 11 minus 6 over 7 minus 5 meters per year at 6 years. So I've interpreted the meaning of this in the context of the problem. That's approximately the rate at which we're growing. On to part B. Part B says explain why there must be at least one time t for 2 less than t less than 10 such that h prime of t is equal to 2. And one of the important parts here is the fact that they told us that h is twice differentiable, which means that h prime is differentiable, which also tells me that h prime is continuous. And this is going to be important because I'm going to be using the intermediate value theorem. In other words, if I can show that at some point h prime of t was greater than 2 and then later on h prime of t was less than 2, then I know that h had to reach 2 somewhere between t1 and t2. And so that's really what we're going to be going for. So I can say that if I take a look at this, I can take a look at what's happening on several of these intervals from 2 to 3, 3 to 5, 5 to 7, and 7 to 10. And I know that I can approximate h prime of t by using that average rate of change. Now, it's not going to be enough to tell me that I know it has to be that, but it kind of gives me the gist that it has to be going from below a value of 2 to above a value of 2, and then I can imply with the continuity and intermediate value theorem. So I could say that h prime of 2.5 is approximately equal to 2 minus 1.5 over 3 minus 2. Well, this is 1/2 and this is 1, so this is 0.5. If I take a look at what's happening at h prime of 4, that's going to be approximately equal to 6 minus 2 over 5 minus 3, which is 2. So my approximate is approximately 2. And we know from the previous problem, h prime of 6 is going to be 11 minus 6 over 7 minus 5, which is 2.5. So I could say that since h prime of t changes value from a value less than 2 to a value greater than 2 by the intermediate value theorem, h prime of t must be equal to 2. So I know that I'm using the continuity, I'm using the intermediate value theorem, and I'm using the fact that I can estimate the instantaneous rate of change using the values in the table. And on to part C. Part C says, using a trapezoidal sum with the 4 subintervals indicated by the data in the table to approximate the average height of the tree over the time interval from 2 less than t less than 10. Remember that my average value of a function is going to be 1 over b minus a times the integral from a to b of my function with respect to time. So in this case, I'm going to be doing my average height is going to be 1 over 10 minus 2 times, and I'm going to have to approximate the integral by using a trapezoid. So for my first trapezoid, my height is going to be 3 minus 2, and my bases are going to be 2 plus 1.5 over 2. That's my first trapezoid. My second trapezoid is going to go from 3 to 5, with my heights going from 6 to 2. My third trapezoid is going to go from 5 to 7, and my heights are going from 11 down to 6. That's a plus. And then my next trapezoid is going to be 10 minus 7 times 15 plus 11 over 2. And so this is my average height of my tree, and keep in mind, because we are talking about units being given, I do need to say that this average height is in meters. So that's part C, and now on to part D. Part D says the height of a tree in meters can be modeled by the function g, given by g of x is equal to 100x over 1 plus x, where x is the diameter of the base of the tree in meters. When the tree is 50 meters tall, the diameter of the base of the tree is increasing at a rate of 0.3 meters per year. And it says, according to this model, what is the rate of change of the height of the tree with respect to time? Well, I'm looking for the rate of change of the tree with respect to time. The problem is this g is a function of x. So what I'm really looking for, that's going to be dg dt, has got to be equal to dg dx times dx dt. That's just the chain rule. And so I'm looking for the change in g with respect to x, which is going to be the derivative of this function, times the change in x with respect to t, which I know is 0.03. So my change in g with respect to t, and I'm going to have to evaluate this at, well, whatever the time is when my height is 50. So if my height is 50, then what I've got here is 50 equals 100x over 1 plus x. This is going to allow me to find out, okay, what is my height, or what is my radius at that time? So I'm going to have 50 minus 50x, or 50, ugly, 50 plus 50x equals 100x. So 100x minus 50x equals 50. And so 50 equals 50x. And so x equals 1 meter. Well, goodness, that makes things really nice. So I want to know what's happening when x equals 1, basically. So I'm evaluating dg dt when x equals 1. So I'm going to have to figure out what the derivative of g is with respect to x. I'm going to use the quotient rule, so the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And it's going to be all of that times dx dt, which is 0.03. And what's nice is x is equal to 1 is something that's really easy to plug in. So dg dt is going to be equal to 2 times 100 minus 100 over 1 plus 1 squared times 0.03. And that's going to be in terms of meters per year, because it's a change in height over time. And of course, nothing wrong with this. I can leave my answer in this form. If I wanted to simplify it, then I would just end up with 0.75? Whatever that calculates out to, but it would be a horrible mistake to actually try and calculate that out, especially in my head like I just did. All right, so that's problem 4.